morning. I'm Katie Cottingham. Welcome to this news briefing from the 252nd National Meeting and Exposition of the American Chemical Society in Philadelphia. We're joined today by Dr. Leticia Bonai from the U.S. Department of Agriculture. She will be talking to us about edible food packaging made from milk proteins. Dr. Bonai?
Hi, good morning. So I am from the USDA Research Lab in Philadelphia, the branch of the Agricultural Research Service. And I am in a research unit called Dairy and Functional Foods. So we focus on dairy products and other functional foods. My team and I have been working on developing an edible packaging film. And the idea behind this, it started, we wanted to utilize excess milk. And the US produces more milk than the population consumes, and usually the excess milk is dried up and stored in bags as non-fat dry milk. And then it sits in warehouses. So the idea was, since casein, the main protein of milk, is known to form some strong structures. It is used in glue, paint, and it has been used in the past for making plastics. One kind of plastic called Galalith. So the idea was to make a thin film with it and to replace potentially plastic wrap. In order to make this, we use calcium caseinate, which is a pure form of casein, which is obtained after precipitating casein from milk with an acid. It is redissolved with a salt, which makes it neutral again. And it makes it soluble again. So then we use the different forms of caseinates, which have different properties, to try and make a broad variety of films. The number one target is to keep it edible. So we have to make sure that we can eat it, so we have no artificial additives in there. It's all food grade. And the idea is to replace some of the plastic packaging that is used for food. For example, the single-serve portions, the drink mixes, and some coatings also, which are used on packaging materials and on food themselves, could very well be replaced with this casein product, which will add extra nutrition because it's a protein. You can also incorporate extra nutrients, flavor, antibacterials, something you want in there. And when it comes to single-serve packages, then you could, if you want, eat the package with the food, so you get extra proteins. Or you can also discard it, and it's instantly biodegradable. So there are several different applications we are thinking of, and we are working on optimizing the different compositions in order to get the best properties for this. The number one best interest of casein films is they are an excellent oxygen barrier, much, much better than regular plastic. About 250 times better, which means that they will block oxygen much longer. Not quite as good as foil, but somewhere intermediate. And so they can keep sensitive foods fresh longer. They also a good grease barrier. So usually the food sensitive to oxygen is a high-fat food. So that will work well for these because it'll be protected both from oxygen and from light also. So they will slow down the degradation and keep the food fresher, tasting fresh longer. For example, nuts, cheese, and some of the other foods of the kind. Sauce pouches, things like this. Maybe cream. Another application is to wrap cheese sticks to try and reduce the immense amount of packaging. We can also make drink pouches, and I brought a sample I'll be showing you. And we can spray it directly on the food, so we're thinking about a cereal bar maybe, and one application we have tried was cereal flakes. We tried spraying Wheaties with our casein suspension mixture, and it kept them crunchy much longer than the regular sugary coating. So you would have extra protein in your cereal, and it will also stay crunchy longer, which is some of the purpose of the sugar usually in cereal, besides the taste. Okay.
Yep. Okay, great. So if that's all, are there any questions? Please wait for the microphone to come and state your name and affiliation before asking your question.
Would you like to see the demonstration first?
Oh, okay.
Yes,
Yes, let's see the demo.
Let me find my spoon.
Okay.
Okay, so I brought some hot water and one of our coffee, single-serve coffee pouches. So it is wrapped in our film, and the film is heat-sealed in a regular heat sealer, so it seals really well. It works really well at wrapping around food. It is flexible, and then we just press the sides with heat, and it melts and forms a good seal. In the lab, this worked really well, so I hope it works here. We tried it a few times in the lab. I hope the water is still hot enough. We'll see. So it goes in there. Well, I have to make it go in there. And there we go. And it's floating a little. I think there's too much air in there. It's breaking up. And there we go. There we go. So after a little stirring, the entire film disappears. So what happens is you just have a little extra protein in your coffee, which is not a bad thing. And I tried it, and taste-wise, it doesn't add any taste, but it adds a slightly creamy mouthfeel, as if you had put some cream. So I don't think we made the pouch big enough this time. It's taking... yeah, the water is not as hot as we had it in the lab, so it's been waiting for a few minutes.
Okay.
So by the time we're done talking, it will probably be done dissolving. So.
Yeah. So it's Kath O'Driscoll from Chemistry and Industry magazine. Thanks for that demonstration. Alex, fun. I mean, talking about eating the protein, how do you think, because I wonder how people will react in terms of consumer acceptability, actually eating packaging. It's just not something we would normally think about. And I wonder whether they would, whether you've done any investigations to find out how consumers would actually react to the idea of eating the material?
Well, not yet. We were in a development phase trying to make the best film possible for the past couple of years. We just started looking into applications and testing them in our lab, which is why this doesn't look perfect yet. We just started a few weeks ago. And so we have not done taste tests yet or consumer panels yet, but we have all the facilities in our research lab. We have a taste kitchen, and we do taste studies where we have blind consumers. And so we do this sort of studies, and that will be down the line, yes.
And what about in terms of hygiene as well, in terms of these products, actually, do they contain any natural antimicrobial activity, the packaging, or say if you're talking about the cheese sticks that you just eat, I'm just wondering if they just come off the shelf, are they going to be hygienic?
So the best property is their oxygen barrier, but then on the water side, they are not good water barriers. Because they're protein and they love water, you see that it dissolves, it's mostly gone now. It's a little light in color because I didn't put enough coffee in it. So they need to be in a secondary packaging. The cheese sticks will have, just as they are now, every single plastic cheese sticks still come in a bag of cheese sticks. So they will still have to come in a separate bag or a tin or a box or something to protect them both from water and from contamination, from soiling.
Yeah. And I was interested, you mentioned that there was this milk excess in the US, because that was going to be one of my questions. I thought that it might compete. I don't know how much of this milk that you actually need to make the packaging, but I guess if this takes off in any big way, how much milk is going to be needed for this type of packaging, and is there enough waste to be able to produce that sort of quantity of packaging?
Well, currently, the casinates we use are being produced commercially. We did not make it in the lab. And they are sold by the pallet. We tried to buy one bag, and we could not, so they are sold by the ton. So it is available. It is produced, and it is used for a few different things. It is not used for packaging yet, but there will be one more use. And also our ultimate goal is to use the non-fat dry milk, which is even lower price and more abundant than the casinates. And so, since the main molecule of dry milk is casein, we're using it as a model to really understand how the casein reacts, so we can make the strongest network with it, the strongest material, because then when we revert back to the dry milk, there will be additional elements in there that will complicate everything. So first we want to make sure we master what the casein does before we add the lactose back in, which is the next most abundant component of dry milk. And the lactose does not like to polymerize. It does not like to make a film. It forms crystals and it gets in the way of film formation. So that will add a lot of extra complication.
Can you say as well something about how the this casein packaging affects shelf life? I always thought it was microbial spoilage that was a problem, but I suppose that's also, how does the oxygen barrier help to enhance shelf life too?
So blocking some of the oxygen will help slow some of the microbial growth. Only aerobic bacteria who depend on oxygen to grow, these ones will be impaired more than in plastic packaging. On the other hand, it lets moisture through. So we will have to do some study. We have a big microbiological team in our lab too, which will be looking into this. We will be starting shelf life studies in our new year right now, which starts this fall. So we're just wrapping up the current studies that we are doing. And we're going to start shelf life, looking at the microbes in aseptic, making the package in an aseptic way, and wrapping different foods in it and see what happens. But so far, the samples we made, we tried some cheese sticks, and we did not have any growth. We had growth in a block of cheese that was wrapped in plastic, but the blocks of cheese we wrapped in our films did not have any mold. So but it's only been a few weeks. So, but that looked promising.
Yeah. And what about the cost compared with conventional packaging as well? How much will this cost by comparison?
Yeah. So this is a thin film, so it will not use very much material, but of course every cent matters to the food industry. So we will also, we just began a 5-year research plan on this project, and so we just completed the first year. So we still have a lot down our pipeline that we'll be looking at. And the modeling of cost is one thing we do. We will be, once we have our favorite process perfected, we will be modeling this with softwares and then modeling all the different costs in there to see exactly how much a square yard of this would cost.
Okay, thank you.
Okay, good. And we have an online question from Helen Tunicliffe, who is with the Chemical Engineer. And she's asking, how is the thin film made from the casein protein?
You want the step-by-step instructions?
I guess a little bit more detail on the process is what you want.
Okay.
Yeah.
So the caseinate comes as a powder, and even though it was remixed with alkali salts, the acid casein wasn't very soluble, not insoluble actually. Once it's remixed, it becomes soluble, but it still doesn't solubilize very quickly. So we mix it with water and we stir for at least 2 hours. If you do not stir enough, you get a pretty sandy material. It's not very homogeneous yet. So we have to stir a long time at room temperature. And then we add some glycerol. Now, glycerol is a grass material. It's not a food, but it's a grass material that is added. It's a plasticizer. Because the casein films, pure casein films, are very brittle. They're extremely strong, and they would snap if you try to fold them to wrap food with it. So the glycerol allows them to be very nice and flexible. This does not crease if you try to fold it. See. So this feels a lot like plastic packaging, plastic wrap. It's a little crunchier. And it's not stretchy. So that's the difference. So it is strong, but it doesn't stretch very much. But it is nice and flexible. So that's how we make those little pouches with them. Then what we do after we add so we add the glycerol first, then we add our protein, then we add any other additives that we want to add, edible additives only. One we have been using is citric pectin, which is a wholesome food component, which is totally edible and even good for you. There's a lot of research on pectin. And the pectin acts as a cross-linker to make our film stronger. So that was some of the research I have been doing, perfecting the formulation, so we have some stronger films that resist ambient conditions the best. Pure casein tends to melt and become sticky if the temperature and the humidity get pretty high. Think of a Louisiana summer, for example. The casein would become a goopy mess. So with the addition of pectin, now we stop that. It's resistant to high temperature and high humidity. Well, not extremely high, but in normal, the warmest, most humid condition you would find in the US, this should be able to handle it, hopefully. We need to test for real in the applications. But in the lab, in our instruments, it behaved well. So then what we do is we spread it on a spreader on a silicon mat. We're using silicon baking sheets because there was a process improvement I came up with, because it allows a thinner film that we can peel very easily. So we get some very nice quality films when they're cast on silicon. And then we let it dry. So we let it dry in normal conditions. We standardize the drying humidity and temperature, so they all have the same kinetics of drying. If you change the drying temperature and humidity, you will probably change the kinetics, and you can change the properties also. They'll be a little different. So we like to have a nice uniform process. And then we let them sit for about a week to make sure that they are equilibrated, because the proteins tend to still move and take a little time to settle into their preferred configuration. And so we start testing everything after about a week.
Okay. Any other questions? I guess what will you do next? What's your very next step?
Well, I started talking about this when Kath asked. We are testing all these applications we have in mind. Mm-hmm. So we will produce large quantities, well, large lab quantities still, but we'll produce a lot of us, our favorite formulations, and wrap all sorts of foods in them. We are testing the spraying on different materials to measure the adhesion. In order to spray, for example, on cardboard, that works really well, on craft paper, and that makes it grease-proof, so that is one application. But we would also like to make it stick to commercial plastic, because then the plastic protects from water, and then our films will protect from oxygen. So then you would have a packaging that does both. And our film will also protect the food from the plastic, so there will be no leaching. So these are the shelf life too. The foods we wrap in our films, we will have them sit at different environmental conditions, and we will have our microbiological team measure the bacterial growth as a function of time. What else is next? The cost analysis will be further down the road. So I think that's
good. We have one last question. So this is from Christine Suh, Office of Public Affairs. Are there certain types of food that the film wouldn't work for, such as acidic foods?
So yes, that's a good question. The casein is well known for being very sensitive to the changes in pH. So which is why we tested coffee, which is a mildly acidic food. I think the pH is around 5. And different formulations of our films did not work in coffee. We have one formulation that dissolves well and there's no chunks. You want to take a look, there's no chunks in there. But this formulation that I'm holding here, this one does not dissolve completely in coffee. It forms some white rubbery chunks at low pH. So so there will be foods in which they will not work with, and if the food is really acidic, it can maybe make it turn white or make it spring a hole. That is possible. So that's why we will be testing a variety of different foods. We do have to keep pH in consideration and be careful with that.
Okay, great. Any other questions? If not, thank you very much for joining us. And the archived version of this session will soon be posted at bit.ly/ACS Live Philadelphia. Please join us for our next press conference today at 1 o'clock on squid-inspired materials for anti-glare screens and encryption. Thank you.
Thank you.